So the discussion here will be on LISA and also the global fit and why we talk about the global fit when we talk about LISA. Currently I'm working in NPIFR on radio astronomy. All of the work that I did that goes into this talk was done with Tyson Littenberg, which we just heard from, in Alabama with Marshall Space Flight Center. So just a brief outline. So the first few minutes of my talk will be the gravitational wave spectrum, LISA, and low frequency gravitational wave sources. Next, we'll learn what global fit means and why we talk about the global fit when talking about LISA specifically. So what makes LISA unique as far as the gravitational wave spectrum is concerned? So lastly, I'll talk about the work towards this end, focusing mostly on the UCB analysis. And when I say UCB, I mean ultra-compact binaries, with particular attention paid to developing our search code, which I broadly call GBMCMC, and that's a galactic binary, MCMC. So I'd like you to keep in mind that the data I've analyzed are publicly available through a group called the LISA Data Challenges, and so is our code. And so you could do your own analysis today if you wanted to. In fact, LISA needs someone to develop an independent pipeline for this type of work. So this is something that Tyson, through the last decade or so, along with a number of other people like Niels Cornish, have developed this code. And so, I just wanted to emphasize that this is work that needs to be done. So we are seeing a rapid development of gravitational wave astronomy, which has the potential to facilitate paradigm shifts in our understanding of the universe. So briefly, the spectrum spans wavelengths of 10 to the 26 centimeter long wavelengths, where one could see the imprint of gravitational waves from the early universe in the CMB, the cosmic microwave background, to relatively short wavelengths of 10 to the 13 centimeters, which LIGO already sees. Recent news from the gravitational wave world, of course, we see that BICEP recently ruled out a number of popular inflationary models. So that paper came out recently. Nanograv, EPTA, and Parkes telescopes also, around the same time, published a paper detailing a common uncorrelated red noise process in their data. So it remains to be seen if these are gravitational waves, but we think that we're seeing the first hints of a gravitational wave background, and Sarah Vigeland is going to tell us more about that later. And also, LISA, we got good news from the decadal survey. If you look at the report, there's maybe 100 references to LISA, and the talk that I'm giving you today, they highlighted that software development is really important for the NASA mission, so that's very exciting. And of course, LIGO, still the talk of the town at NPIFR, is the recent discovery of, I know it's not new news, but they're still talking about the discovery of a heavy neutron star, a black hole, and a mass black hole. So next, a few words about LISA detector and sources to motivate our discussion for parameter estimation in the milli-Hertz wavelength regime. So briefly, what is LISA? LISA will measure the optical path length of freely falling test masses. They follow geodesic trajectories. There will be 3 identical science crafts separated by about 2.5 million kilometers. Laser interferometry is used to monitor the distance between the test mass. And it's an all-sky monitor, which will be important for later when we talk about the global fit. LISA will be in an Earth-trailing heliocentric orbit about 50 to 60 kilometers, a million kilometers from Earth. So the scale is very large. All right, LISA sources. So of course, there's stochastic gravitational wave background. We'll hear some of that from Ariana later for ground and space-based detectors. And that covers the full frequency band. And then we have late time coalescence and mergers from massive black hole binaries. Everyone knows this gwplotter.com. It's very handy. Also, we have stellar intermediate and extreme mass ratio in spirals. And we can add more sources yet. Galactic ultra-compact binaries, mostly 2 white dwarfs. And then, of course, we have unanticipated signals. So it really is very important that we understand how to search for and extract as many of these signals as we can so we can find the needle in the haystack. So now that we have the big picture of LISA and its sources, we can begin to look at the global fit. When we talk about LISA and source detection, we start to think about how so many of the sources will be overlapping. Parameter space is large. So how do we reasonably sample such a huge parameter space? The figure on the right is from the LISA proposal. It shows us a power spectral density for the different source types in the LISA measurement band to again give a sense of how rich the data are. The LISA data stream will contain a large and a priori unknown number of sources. And many sources will be overlapping with one another in time and frequency. And while most of the individual overlap between pairs of sources is small, meaning they could be well localized within a specific frequency range, the large number of sources means that there are many small overlaps which can compound. And so these can accumulate if you just don't want to ignore this fact. So again, the number of sources is large. Sources are overlapping in time and frequency. Small overlap between sources. So now we can look at, before discussing the global fit, we can look at the work being done by data analysis groups at large towards parameter estimation for LISA. We still have a decade to figure this out, but there's still a lot of work to be done. So what are the LISA data challenges? The purpose of these challenges is to facilitate and coordinate the development of data analysis pipelines and signal waveforms. We want to improve existing algorithms. We want to create new algorithms, which I alluded to at the beginning of the talk, independent algorithms. And we want to generate a common platform to compare and contrast the performance of these pipelines, address the science requirements, and the overarching goal, of course, is to develop mission-ready intent data analysis pipelines. And so you can basically find different groups focused on different aspects, but the LISA data challenges specifically are focused on source extraction in a noisy data stream. So the Radler data challenge was challenge 1, if you will. The 2018, it was issued in 2018, and it comprises 4 separate challenges. Each contains one type of source. We have stochastic signals, single massive binary black holes, single MREs, or extreme mass ratio in spirals, and galactic binaries. There's another data challenge that's out now, challenge 2. And so they want to tackle mild source confusion and idealize instrument noise. So there's 2 main types of data sets. Each contains Gaussian instrumental noise and simulated waveforms from 30 million galactic white dwarf binaries, 17 known or verification binaries. That means they're observed electromagnetically, and we should expect to see them in the LISA data stream. And they've thrown those into the data as well. Merging massive black hole binaries with parameters from an astrophysical model. The first data set includes the full specification used to generate it. So that means that the key file has the source parameters, a description of the instrument, and also LISA's orbit, et cetera. So that's in the key file. And then the second data set is blinded. So the level of instrument noise, the number of sources, et cetera, is an unknown. So the one way we envision searching the LISA data stream is with Markov chain Monte Carlo algorithms. A strong point of MCMC, which Tyson alluded to earlier, is that there's a finite probability of moving away from a favorable location in parameter space so that you can avoid getting stuck on local maximums as likelihood surface. So the analysis always converges, but it might take a while. You have a one-stop shop for detection, characterization, and quantifying the confidence. And you can stochastically sample between the different models with a reverse jump MCMC. So with an MCMC sampler, there's a straightforward way of also sampling over different models, like I just alluded to. This is critical for LISA when we have such a large parameter space. With other fixed dimension sampling algorithms, it would be impractical to sufficiently sample all of parameter space. So the question is how to efficiently sample over such a large parameter space. And so for that, we look to blocked Gibbs sampling. So this means that only a subset of parameters are updated in each step of the chain. And so the big picture is that you would have these different blocks that focus on different types of sources. And so I'll show you a little bit about UCB analysis, but the idea is to trade information between each block periodically as you run your MCMC. So a little bit more detail. We ask, what is block Gibbs sampling? So we imagine two blocks of parameters A and B. Here, they're represented on the 2D plane, but A and B can both represent several individual parameters. The Gibbs sampling approach is to hold one block fixed, say A, and only sample over a block B. And then alternatively, to hold B fixed and sample over A, continue, etc. So as suggested in the drawing, the block Gibbs approach has pretty horrible convergence when the block is, when you have highly correlated data. But the actual correlation between individual sources is generally small. So what we really need the global fit for is to account for uncertainties in each of these blocks. So this strategy allows individual blocks to be developed independently with the agreed upon protocol between the different blocks. It also lends itself to being broadly parallelized, and this we can take advantage of the distributed computing model currently favored by the LDPG, LISA Data Processing Group. Another advantage is the modular design, which I showed you the graphic for earlier, so you can add and remove and focus on different blocks as you develop the code. So here's a big picture of how we can envision this analysis going when LISA flies. So of course, all of these individual blocks are currently under development now. And now the work is starting to begin to have these different elements talk to each other. And so the green canisters represent trading information between each block. The algorithm will cycle through many updates for each block, and then it would be reformatted for the final data product. The L2 data product is the final data product. So now that you see the big picture, I'll share with you what we have done and what we're currently working on. So again, we are using publicly available software called LDA Soft as our starting point. It was created by Tyson, and many of us have helped develop various parts of the algorithm over the years. It uses a reverse jump MCMC, which is it allows trans-dimensional moves between different models, which Tyson talked about earlier. For the analysis, I did the Fourier domain. In the Fourier domain, the data are segmented and analyze individually in an embarrassingly parallel way. That just means that we analyze many segments in parallel, but there's no communication between different segments. But work in that direction is also being done now. So I won't focus on the mechanics of the MCMC itself. The parameter model is pretty basic. We just have 8 parameters. So some of you might know that black hole binaries, for example, might utilize a 17 parameter model. Here we have a reduced parameter space. The waveforms are understood and well known. So I'll focus on the output, focusing on the observer view and the developer view. For both viewpoints, the chain data need to be sorted into catalog detections. So this is the standard output for the frequency amplitude plane. And so you see here that, especially when you look at the 12-month data, you can start to see individual blobs emerge. These are individual, would-be individual catalog detections. So we developed a tool to cycle through the chain data. We generate waveforms for every sample in the chain and use the overlap interval between different samples to create and then group catalog entries. And so we realized early on this approach is much more efficient than generic clustering algorithms. So we take advantage of the fact that if we have a set of parameters, then we know the waveform and we can calculate the overlap between different samples to group the data. And so when we've done this, here you see again the original chain data. When we've done this, you can see that we've now sampled our data with the catalog maker tool. So this is a look at one-month analysis for the same analysis segment I showed here. So the top graphs are the power spectral density for the A and the E channels. We add the catalog waveforms that we found in the middle graphs. And at the bottom, we have, the frequency amplitude plane and the sky location. So this is only 1 month of data, so you can see that we're not doing very good at localizing the source. So you imagine that if you're the observer, these are the types of plots you might see after analyzing just a month of data. So we move to 3 months of data. And we've used the catalog detection from the 1 month analysis as a proposal for the 3 month analysis. And so you see here for 3 months, the observer would notice that one of the sources has a history, which you can see there in red, with the 1 month catalog detection. But the other 2 that we found at 1 month have now disappeared. Namely, we did not have a catalog detection at those frequencies. But we move on to 6 months of data, and the colors for the plots are the same, meaning that when you move to a longer analysis segment, you can use the waveform to correlate the data between different observation times and see which catalog detections at 6 months, for example, have a history with the 3 month catalog. And so that's what the colors correspond to. So here you can see the 2 more sources at the high frequency range of my analysis segment showed back up. And we also detected 2 lower signal to noise sources at the leftmost edge of the plot. And you can start to see that we start to see exactly where sources are localized, also in frequency and sky location. So we move on to 12 months, and it's the same story, except now we're doing even better, localizing the source in the sky. And this is 24 months. And we'll revisit this particular analysis segment as an interesting corner case, because you can see that at 6 months, we've detected, if you can barely see, there's a green source that's it's very much below these bright detections, the red-orange detections. There's a green source there. And that showed up at 6 months, but it disappeared at 12 months. We found another source in 12 months. And it reappeared at 24 months. And so these are the things you start to notice from a developer standpoint that we want to sort of sort out before LISA flies. So this is, again, the observer's view. So we have catalog detection, 2D posterior on the sky location, the leftmost plane. This is in galactic coordinates. And also you can calculate your power spectral density, where the red is your original data. The green is the noise model, and the blue is the residual after you subtracted the data, subtracted the sources from your data. Also, focusing a little bit on the observer view, one thing the observer will want to do is find out which sources they should focus on for follow-up observations. So we would look for sources that are well localized in space, that are spinning up and eclipsing. So those are prime targets for follow-up observations. And so this is one catalog detection that we identified in the LDC data. And the table on the right shows you how many of these sources we found. So I want to speak about the developer view. This is where I spend most of my time. So the goal isn't really to fine-tune your algorithm so that you can find as many of the LDC injections as possible, meaning you don't see how well you did and just fine-tune your code for that particular data set. So the goal really, from the developer standpoint, is to use the injection key to determine what areas of your code need improvement. And so that's what I've spent most of my time doing recently. Some improvements to the code have already been done. Tyson had a summer student who took the GBMCMC code and parallelized it so that he wrote the code such that different segments will also be able to communicate with each other. So the way that we originally did this analysis was in an embarrassing parallel way, and now this code is well on its way to having individual segments communicate with each other and trade information. So in that direction, we'll look at how well we did recovering the LDC injections. For the post-analysis, we focus on the frequencies above 5 millihertz, where our confusion noise is greatly reduced. In that region, above 5 millihertz, we expect to have a good recovery rate. If you look below 5 millihertz, each segment might have hundreds of sources. So there's a lot more confusion noise below 5 millihertz. So here, we're computing the overlap between the catalog injections with the LDC injections. And so in this right plot, you can see how many of these sources we think are confused, meaning that they might match more than one LDC injection. How many of the sources are unambiguous, meaning they have a one-to-one match with an LDC injection. Usually that means it's met our threshold for saying that it is a one-to-one match. And so we usually set that match value to be 0.5. And also we have a small subset of the detections, which are false alarms, meaning that they had no match with an LDC injection. And so in real life, you're not going to have this information. You will have an idea of which sources are confused, which I showed you earlier, some confused sources that have frequency range of that segment. But in real life, you're not going to know which sources actually are a galactic binary and which are not. So it's important for us to develop the code such that we can reduce the number of false alarms. So I want to focus on a corner case. So this segment we visited earlier, or I pointed out that you saw the frequency amplitude graph before, but I pointed out that, I guess I can see those. It's 6 months that you can see right around 5.209 millihertz, which is this green blob on the right of the 6-month graph. You see it's disappeared at 12 months. And again, it's reappeared at 24 months. And so you can see the waveform in gray. I've added all of the catalog detections, this gray curve, and the red is the original data. And the source in question that we saw at 6 months disappeared at 12 is in blue. And you see when we did the 24-month analysis, we recovered that source. But there is more complicated corner cases, and one that I've been really focusing on recently is a segment where each time I run the code for this particular segment, keep in mind that I looked through all of the cases, or looked through every single catalog detection above 5 millihertz, and I just picked out ones that looked like they were confused for the purposes of developing the code. And so you can see this is the frequency amplitude plane for a 2-year analysis repeated 9 times. And the first analysis at the top was the original one, where I used proposals from the 12-month analysis. And if you look at the leftmost region where there's an orange and a green source, this is the region that's basically the lowest signal-to-noise source in the teens. And so this is a region where we have some confusion. I run the code multiple times, and each time in that particular region, you can see that I get a different answer each time, which could mean that the answer simply hasn't converged. And so you would think that adding more data or adding more time to your analysis might help you sort this out. So I doubled the amount of steps in my MCMC, and you can see that I'm still having issues with convergence in that particular region. There's also, you notice, a very bright source in the data. And so it could be that a lot of time is being spent fitting this very bright source that's like signal-to-noise of 700 or so, and less time is spent fitting this low signal-to-noise source. And so we look at the sky location plane. This is interesting because I noticed that the frequency of some of these blobs had split into 2 modes. And so and if you look to the right at the sky location, you can also see 2 modes popping up as well. You can't quite see it in frequency because it's too small. But essentially, the sampler was unable to locate the source, and the frequency becomes degenerate because of that, because of those 2 different modes in the sky location. Thank you.